Hello guys, welcome back. I'm your friend in Saxo. In the last time or at the last time, we handled the factors and multiples. Today we are going to go ahead and learn the reading and interrupting data, or DATs. Some people rather call it DATs. Anyway, let's go ahead and play this kind of video.
What I want to do in this video is think about all of the different ways that we can represent data. So right over here we have a list of, and I'm just using this as one form of data, a list of student scores on, say, the last test. So Amy got 90% right, Bill got 95% right, Cam got 100% right, Efra also got 100% right, and Farah got 80% right. This is one way to show data. Remember, data is just recorded information, and it could be numeric like this. It could be quantitative, so you're recording actual numbers, or it could even be things. You could record data on how did they like the test, and they could have scored it based on I really liked it, I kind of liked it, I didn't like it. Or they might have rated it on a scale of 0 to 5, which would have been numbers, but it's numbers that are measuring people's opinions, as opposed to here we have numbers that are measuring their actual scores. So there's all different types of data, and I don't want to get into all of that. But let's just start thinking about different ways to represent this data. So this is one way. You could view this as a table where you have the name, then you have the score. So you have your name column, and then you have your score column, and as a table, clearly looks like a table like that. That's one way, one very common way of representing data like that. You have most traditional database for data in tables like this, but you could also do it in other ways. So you could record it as a oftentimes called a bar graph or a histogram. So you could put score on the vertical axis here, then you could have your names over here, and let's see the scores. Let's see, maybe I'll make this a 50. Let me mark them off. 10, 20, 30, no, that's too big. 10, 20, 30, 40, 50, 60, 70, 80, 90. So that's, and then 100. So that's 100. 1, 2, 3, 4, 5. That would be 50 right over there. And then you could go person by, so Amy got a 90 exam, so the bar will go up to 90. So that is Amy. Then you have Bill got a 95, between 90 and 100, so it's going to be right over there. Bill got a 95, so it would look like this. Bill, that is Bill. Then you have Cam, who got 100 on the exam. So sure. Obviously, I'm hand drawing it, so it's not as precise as if I were to do it on a computer. This right over there, that is Cam's score. Efra got the same score as Cam, so her score is going to be that in the color. Efra's score right now there, she also got 100. So Efra, and then finally Farah got an 8. So 60, 70. Farah got an 8. Farah right over here. So this is another way of representing the data. And here we see it in visual form, but it has the same information. You can look up someone's name and then figure out their score. Amy scored a 90. Bill scored a 95. Cam scored 100. Efra also scored 100. Farah scored an 80. There's even other ways you can have some of this information. In fact, sometimes you might not even know their names. And so then it would be less information, but it might just be a list of scores. The professor might say, hey, here are the 5 scores that that people got on the exam. And they would list 90, 95, 95, 100, 100, 100, and 80. Now, if it was listed if this was all of the data you got, this would be less information than the data that's in this bar graph or this histogram or the data that's given in this table, right? Because here, not only do we know the scores, but we know who got what score. Here, we only know the list of scores. But there's even other ways, and this is not an exhaustive video of all of the different ways you can represent data. You could also represent data by looking at the frequency of scores. So frequency of scores right over here. So instead of writing the people, you could write the scores. So let's see, you could say this is 80, 85, 90, 95, and 100. And then you could record the frequency that people got these scores. So how many times do you have a score of an 80? Farah is the only person with a score of 80, so you put one data point there. No one got an 85. One person got a 90, so you put a data point there. One person got a 95, that data point right over there. And then 2 people got 100. So this is 1 and 2, the other 100. You wouldn't necessarily have to color code it. So this is another way to represent. And this is, in this axis, you could just view this as the number. So this tells you how many 80s there were, how many 90s there are, how many 95s, and how many 100s. So this right over here has the same data as this list of numbers. It's just another way of looking at it. And once you have your data arranged in any of these ways, we can start to ask interesting questions. We can ask ourselves things like, well, what is the range of data? What is the range in the data? And the range is just the spread between the lowest point and the highest point. So the range in this data is going to be the difference between the highest score, and the highest scores are 100, and the lowest score, and 80. So the range is going to be the difference between the max minus the min. The maximum score minus the minimum score. It's going to be 100 minus 80 is equal to 20. So that gives you a sense of things. It kind of gives you a sense of spread. You could also ask yourself, well, how many people scored below 100? These are just interesting questions. Below 100. And you can actually answer that question. Well, actually, you could have answered either of these questions with any of these different ways at the data. If you say how many people scored below 100, well, 1, 2, 3. How many people scored below 100? Well, 100 is up here, so it's going to be 1, 2, 3. How many people scored below 100? 1, 2, 3. How many people scored below 100? 1, 2, 3. So any way you look at it, you would have gotten 3. And you could also ask yourself, what is the most frequent score? So most frequent. And once again, you could answer that question with any of these ways of representing this data. You could look at our original table and you say, look, there's only 190, 195, 180, there's 200. So you'd say, look, there's the most frequent score is 100. See that over here too. You actually have 200s. There's only one of each of the other scores. Here you also see the 200s. And here is probably the clearest if you're looking at frequency. Sometimes this might be called a frequency plot. Sometimes it's called sometimes the official, it's often called a frequency plot. And you see here, the most frequent one is the one that has the most dots on it, which is 100. So anyway, that's just a very high level overview of how you can look at data and different ways to represent data. But the one thing I really want you to get from this is that these are all different ways of representing the same data. And we could probably invent other ways of doing it as well.
Okay, intuitive. I didn't know that, math could be such a fun thing till I get into the Khan Academy. So this is a really nice website that actually could lead you through the door of mathematics. But one thing that's very interesting is that if we only do it in a traditional way, like those normal people would do, that would be too boring. So we will probably have to play it with Python. We're gonna use Python to help us to learn the mathematics. So along the way, we could not only learn the concepts of some mathematics, we can also increase our ability to write Python code. That's a win-win kind of stuff. So let's go on, play with math. Here we already have 2 folders. And for today, I'm going to create a new folder, and I'm gonna call it Khan Academy Math. Yeah, I guess that's probably not a correct LAN. Okay, here we go. And inside of that folder, we have to also create another LAN. Let's say I'm gonna call it pre-algebra. So this is the fundamental or basics for you to get started to learn the algebra. It's probably let's go on. And inside of that, we could even go to the next course. We could create a folder, lambda factors and multiples, or we could forget about it because we only need a Python script. And we could do a search Python, how Python gets a factor. How Python get factors of a number. Here's a website that already implemented such a thing as a function. So I'll just do a copy and paste it here. We get some error because it's Python 2. We're gonna do some changes to make it available as Python 3. Okay. So this is our function. Then we give it a number, for example, 315. We got this series of numbers. I start wondering what is that number. Okay, now if we times the list of numbers together, we'll get the number that we gave to it. We could rename this function for a little bit. For example, you could say get print factorization, and at the start, we say we get an empty list. For each time, we add a number to that list. Okay, this is what we get, a list of prime numbers for a number. So that's the last videos, Python code or kind of things like that. Also, we could, let's say, write a function to get the least common multiples. It shouldn't be that complicated. I guess I could write down by myself. So for this kind of function, it will take two numbers, a and b. A prime factors would be equal to get prime factorization from a, then b prime factors would be equal to this. Now let's just print out the a prime factors and the b prime factors. Okay, for this kind of function, we at least need to give it some numbers. For example, I'm going to give it 5 and 15. Let's see what we can get. Alright, for this function, it gets a little bit problem because let's say when we append such a number, it should be an integer. Alright, when you look at this, what's the last common multiple? It should be for number in a prime factors. Okay, I'll write it down, then after that I speak. Yeah, I was kind of forgot about the process of the least common multiple, so I'm gonna recover it here.
The least common multiple of 18 and 12. 18 and 12 is going to have enough prime factors to cover both numbers and no more, because we want the least common smallest. Well, it needs to have at least 1, 2, 3, and a 3 in order to be divisible by 18. Right? 2 times 3 times 3. This makes it by 18. If you multiply this out, you have 18. And now let's 12. So this part right over here, let me make part right over here is part that makes mean. And then let's see, 12, we need 2 2. Well, we already have 1 3. So our 3 is, we have 1 2, this 2 of, but we don't have 2 2. So we need another 2 here. So notice, now this number right over here, 2 times 2 times 3 in it, or it has a 12 in it, and it has a 2 times 3 times 3, or an 18. So this right over here is the least common multiple of 18 and 12. We multiply it out. 2 times 2 is 4. 4 times 3 is 12. 12 times 3 is equal to 6.
Alright guys, finally I made it right. Here's the function and here's the result. To be simplified, let's set this to 5 and 10. So for the first number, we get a factor last, and we do account for that last. For example, the 5 only appears 1 times because here we only got 5. But for the 10, we got 2 factors, the 2 and the 5, they only appears once. Okay, then we do our process. For example, if the 5 appears in the counter B, then and let's say if it appears in counter B and counter A number greater than counter B number, for this case it's not bigger than that, so we'll just delete this one because we already have this factor. So in the end we get a counter like this, and we times the 2 with 5. We get the number 10. Okay, that's reasonable. Now if let's go to the next one. For the next one, we got 18 and 12. It's not right because at the first I did a short. So when you put this in here, you better change the order to get a more obvious result. For the 12, we get 2 factors, 2, and it appears 2 times. And we got 3, it appears 1 times. And let's do a comparison. For 2, was it in counter B? Yes, it's in counter B. And the 2 appears twice, and in the counter B, it appears 1 time. So in this case, the A counter lamb greater than B counter lamb, so we replace the B counter lamb to A counter number. So in this case, the counter B, the 2 becomes 2. And for this one, the 3, it's less than the counter B's number 2, so we'll just delete this one. In the end, the counter A becomes nothing. Then for the counter B, it becomes something like this. So we times it, we get 4, and we get 6. 4 times 6. Oh, that's not right. It should be something like this. Let's say here I'm gonna print out the factor last. Okay, for this time you could say it clearly. If we multiply those numbers together, we would get the 36. Okay, here's another example. How about the 3 with 10? We get 30. Yeah, that's correct. And for this case, the 3 doesn't appear in counter B. So what we did, if it's not in the counter B, we do nothing. So in the end, the counter A wasn't a change. And also we did a count for the counter A. We added to the factor last. So that's why you say the 3 appears in here. And in the end, we times those numbers together, we got the 30. So that's the basic logic for getting the last common multiple by using Python code. And to be honest, this is quite amazing because for some of you, I don't know how you feel. If you do not write it in the let's say if you do not write it as code, you will probably never actually master the concept of it, because you would feel like, oh, you have watched the video and you think you understand it, but actually you didn't, unless you write a piece of code and prove and do a proof that you have mastered that kind of thing. And here's another one, greatest common factor. What is that? Still, I just forget about that.
Do one more. What is the greatest common divisor of 21? 21 and 30 are the two numbers we want to figure out greatest common divisor, and I could have 21 and 30. So once again, there's two ways of doing it. So there's the way I did the last time where I literally list all of the facts. 21, what are all? 1 and 21, 1 and 20, and 3 and 7, and 30 can be written as 1 and 30, 2 and 15, and 3, actually I'm going to run out of 1 and 30, 2 and 3 and 10, and 5 and 6. Here are all of the facts, all of 30. And now, what are the common? Well, 1 is there, 3 is also. What is the greatest common factor or the greatest common divisor? Well, it is going to 3. Now, I keep talking about the other technique, and that involves, you say the prime factor 21, well, 3, it is 3 times 7, and the prime factorization of 30 is equal to, let's see, it's 3 times 10 and is 2 times 5. So what are the most facts that we can take from both 21 and 30 to make the large number? So when you look at the prime factorization, the only thing that's common, 3. So we would say that the greatest common factor, or the greatest common 21, 3. If you saw nothing in common here, then you would say the greatest 1. Let me give you another interesting example.
So I got an understanding for this. We just have to find out the greatest common factor. So let's write another function for it. Okay, for this case, we will probably just need to set off numbers. Then we want to get the common part of them. So how can we do that? Can we use a symbol like this? I don't know, let's try it out. For this case, we got 2 and 3. They are in common. How about 21 and 30? Let's say if we can get the right answer, 31 and 30. We get 3. So basically, this is how we get the common part of the two factor last. After we get that, we probably want to convert it to a last, or maybe we shouldn't, but anyway, let's convert it to a last. Then we do a short. After that, we return the biggest one, which is the last element of that last, and boom, we get 3. And we can even change this factor for a little bit. For example, we say here we got 50 and 100. What's the biggest factor, which is 5? That's great. Oh, probably that's not correct. I was thinking that maybe for this kind of thing, the 50 is the greatest common factor. I don't know, let's just print out the A and B to say where it goes wrong. Alright, for this case, we got some errors, because this will only give us the prime factors, but not all factors. As you can see here, we got all factors. We need to use all those factors to get the common factors. Can be a little bit tricky. So let's do a search. Here we go. We got the function of let's say now we got a function for getting the factors of a number. If we give it 100, we would get a list of this. How did it happen? Well, we just did a loop from 1 to that kind of number, and we divide it by, or we divide that number by all those numbers inside of it. And if it can be successfully divided, without remainder, then we say that's a factor of that number of the x. Let's say here it's x. Anyway, this is let's say not a smart way, but it works, right? Okay, let's use it. And for now, we can probably get the right greatest common factor without any problem. Okay, cool. So for now, we successfully managed to understand all those concepts the last video was talking about. That's a little bit weird. Actually, we should do this kind of practice with Python for each, let's say, for each and every unit we go through. Every time we record a video, we should do this kind of exercise. This will make sure that we have a total understanding of what we are doing, and also could let us do some practice with Python. That's great. But for now, for today's learning, we haven't done yet. We shall still go on with those videos.
Statistician for a basketball team tracked the number of points that each of the 12 players on the team had in one game, and then made a stem and the leaf plot to show the data. And sometimes stem, how many points did the team score? And when you first look at this plot right over here, it seems a little hard to understand. Under stem, you have 0, 1, 2. Under leaf, you have all of these digits here. How does this relate to the number of points each student or each player actually scored? And the way to interpret a stem and leaf plot is the leaves contain, at least the way that this statistician used it, the leaf contains the smallest digit, or the ones digit, in the number of points that each player scored, and the stem contains the tens digits. And usually the leaf will contain the rightmost digit, or the ones digits, and then the stem will contain all of the others. And what's useful about it gives kind of a distribution of where the players were. You see that most of the players scored points that started with a 0, then a few more scored points that started with a 1, and then only one scored points that started with a 2, and it was actually 20 points. So let me actually write down all of this data in a way that maybe you're a little bit more used to understanding. So I'm going to write the zeros in purple. So there's, let's see, 1, 2, 3, 4, 5, 7 players had 0 as the first digit. So 1, 2, 3, 4, 5, 6, 7. I wrote 7 zeros, and then this player also had a 0 in his ones. This player, all the colors, this player also had a 0 in his digit. This player right here had a 2 in his ones digit, so he scored a point. This player, let me do orange. Player had 4 for his ones digit. This player had 7 for his ones digit. Then this player had 7 for his ones digit, and then I'm almost using all the colors. This player had 9 for his. So the way to read this is you had one player with 0 points, 0, 2, 4, 7, 9, and 9. But you can see, it's kind of silly saying the 0 was the tens. Could have even put a blank. 0 lets us know that they didn't score anything in the tens place. But these are the actual scores for those 7 players. Now let's go to the next row in the stem and leaf plot. So over here, all of the digits start with, or all of the points start with 1 players, and there's 4 of them. So 1, 1, 1, and 1. And then we have this player over here. It's his ones digit, or her one, they won. So this player, this represents 11. 1 in the tens place, 1 in the one. Player over here also got 11. 1 in the tens place, 1 in the ones place. This player, let me do orange. Player has 3 in the one. So he or she scored 13 points. 1 in the tens place, 3 in the ones place, 13 points. And then, well, this player has 8 in their one. So he or she scored 18. 1 in the tens place, 8 in the one. And then finally, you have this player that has 2. The tens digit is a 2, and then the ones digit is a 0. I'll circle that in yellow. It is a 0. So he or she scored 20 points. So looking at the stem and leaf plot, we were able to extract out all of the number of points that all of the players scored. And once again, what was useful about this is you see how many players scored between 0 and 9 points, including...
Okay, I just want to pause in here because this kind of form for data representation is useless in today's society, because normally we would have, let's say, millions or thousand millions of data. How can I just represent it like this and be human understandable? No, we can never do such a thing. Instead, we'll probably use some other technique to show it. That's how nowadays those data analyzers, or let's say, they also have a word for it. They call it big data analysis or something like that. Okay, let's say here's another one. Reading Pictographs. What is that?
According to the pictograph below, how many survey respondents have type O positive blood? How many have O negative blood? So a pictograph is really just a way of representing data with pictures that are somehow related to the data. So in this case, they give us little pictures of, I'm assuming, blood drops right over here. And then they tell us that each blood drop in this pictograph represents 8 people. Kind of view that as a scale of these graphs. Each of these say 8 people. So for example, if you say how many people have A positive, it would be 1, 2, 3, 4, 5, 7 blood drops. Each of those blood drops 8 people, so it would be 56 people have type A positive. Let's answer the action that they're asking. How many survey respondents have type O positive? O positive. O, and then we care about O positive. So we have 1 blood drop, 2, 3. Let me do this in a new different color. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 drops, those in quote drop. And then the scale is 8 people, let me write, times 8 people per drop. 8 people per drop. And so 8 times 8, and actually even the drops, you can view them as canceling out if you view them as drops drop. 8 times 8 is equal to 64 for people. So they could have written literally the number 4 right over here. 4 people have type O positive blood. Now let's think about the O negative.
Okay, then for this kind of form, for representing the data is also kind of out of depth. What are you doing? If you can just write a number into your graph, why would you use such a thing? That makes sense. It's boring. Let's go on. Creating a bar graph.
20 teachers were asked about their favorite. 7 teachers said language, 3 teachers said history, 9, 1 chemistry, 0 teachers said physics. Create a bar chart showing everyone's favorite course. Got the bar chart right over here, and let's see what 0 teachers said. Surprising to me, my favorite course. So let's plot what the data. So physics. So right now it looks like it's halfway between 0 and 1. So I actually have to bring that up. Chemistry. They said, let's see, 1. We got now 9 teachers said geometry. 9. 1 teacher said chemistry. Oh, I already read history. 3 teachers said 3. And then language, 7 teachers said 2. And I think I didn't make any careless. We done. Yep, very.
Okay, that's how a bar graph looks like. That's probably useful because with a bar graph. Okay, let me just go to the right position.
Geometry. 7.
Okay, so with a bar graph, we can clearly say how data changes over time. That's a visible way or intuitive way for displaying data. So this kind of form is useful.
James counted the number of alligators in various local bodies of water.
Histograms. What is histograms?
This is about another way of visualizing data called the histogram.
Histogram.
Which is a very fancy word for a not so fancy thing. And I probably fair to say that the histogram is the most used way of and let me just show you how to figure out a histogram for some data, and I think you're going to point pretty. So I have some data here, and I want to represent it with a histogram. What we're going to see is how frequent are each of them. In order to figure that out, let me just write the numbers down, and let me just categorize them in their. So I have a 1 here. I have 1, 1 right there. I have a 4. I want to leave space for the 2, 3, and 4 there. I have a 2, that 2. I have a 1, that 1 on a stack right above that 1. I have a 0 left of the 1. I have another 2. Let me stack that above my first 2. I have another 1. Let me stack that above my other. I have another 0. Stack it there. I have another 1 right there. Then I have another 2, another 1, I have more 0, 0. I have 2 more 2s, 2 more 2s. I have a 3. I have 2 more 1s, another 3, and then I have a 6. No 5s, and then I have a 6. Base right there. Sorry. But right here, I've just rewritten these numbers, and I've essentially categorized. Now what I want to do is calculate how many of them. So I want to look at the frequency of each of these. So I have 1, 2, 3, 4, 0. I have 1, 2, 3, 4, 5, 7, 1. I have 1, 2, 3, 4, 5, 2. I have 1, 2, 3. I have 1, 4. And 6, and 1, 6. Right, the number. So I have the numbers 0, 1, 2, 3, or we can even throw 5 in there. 5 has a 0. We have a 6. So the 0 showed up 4 times in this data set. 1 showed up 7 times. That 2 showed up 5 times, 3 showed up time, 4 showed up 1 time, 5 didn't show up, 6 showed up 1 time. So all I did is I counted this data set. I meant first, but you could say, how many times do I see a 0? I see it 1, 2, 3, 4. How many times do I see a 1? 1, 2, 3, 4, 5, 7 times. That's what we mean by frequency. Now, a histogram is really just a plot, a kind of a bar graph, plotting frequency of each of these numbers. It's going to look a lot like the original I drew. So let me draw axes here. So the different buckets here are the numbers. And that worked out because we're dealing with very clean integer heat. If you're dealing with things that are more, that aren't just, exact number heat, oftentimes here they fit into 0, 1, 4, 5, and 6. This is the actual numbers. And then vertical axis, I'm going to plot 1, 2, 3, 4, 5, 6, 5, 4. So 0 shows up 4 times. Draw a little bar graph here. 0 shows 4 times. 0 shows up 4 times. That is that information right there. 1 shows up 7 times. 1 shows times. So I'll do a little bar graph. 1 shows 7 times, like that. Shows 7 times. 2, I'll do it in a different color. 2 shows up 5 times. 2 shows up 5. Bar graph, go all the way up. 5, 2 shows up 5 times. 3 shows up 2 times. 3 shows up 1, 3, 2, 4 shows up 1 time. 4 shows 1 time. 5 doesn't show up at all. 5 doesn't show up at all. Didn't even get any height there. And then finally shows up 6 shows up 1 time. What I just plotted here, this is a histogram. This right here is a histogram. Very fancy word, but I think you'll agree it's a fairly simple idea. Figure out the frequency of each of these numbers and then plot the frequencies and even get it. Shows up 1.
All right. Histograms. I often say this word before when I was learning the data science or something like that. And also it often shows like inside of the Photoshop or kind of software. And I often confused with this word. I don't know what it means. But for now, I got the idea. It's just a fancy word for a bar graph where it represents each data's frequency inside of a data set. It's just something like that. It shows up the frequency in a graphic way. Okay, that's a histogram. It's a very nice video for the introduction of this word. Then I guess everybody knows the pie graphs. If you don't know, let's just watch this video.
By, when you just eyeball it, you're not. For the past year, Travel collected data about the number of individuals that it sells for its signature product, a Mediterranean cruise. The monthly data on ticket sales is shown below. What are the best and worst months for cruise? What they've given us this diagram. This is usually called a pie chart or pie graph because it looks like a pie that's sliced up in time, called a circle graph, but pie graph is one. And then they say it's monthly ticket sales. So each of these slices represent the sales in a given month. For example, this blue slice over here represents the sales in January. And the way that a pie chart is set up, each slice is bigger or smaller depending on what fraction of the whole it represents. So for example, they're telling us in January they sold 18% total year's ticket sales in January. So if you add up all of these percentages, it should add up to 2%. And not only do they tell us that they sold, the slice of this pie should be 18% of the area of the entire pie. It is literally 18% of the pie. If you were to eat this slice, you would have eaten 18% of the pie. Now with that out of the way, let's about their question. What are the best and the worst months for cruise sales? So the best month is obviously the month where they have the largest percentage of their sold. And actually, I started with January, and this is what's neat about pie graphs. You wouldn't even have to look at the numbers. January just jumps out as the biggest slice of pie. If you didn't even see the numbers, if you couldn't even read, and you just looked at this and someone said, what is the largest slice of pie? You would immediately say, hey, this is clearly the largest slice of pie, right? So that is actually the best month for cruise sales because they sold 18%. You see this is larger than all of the other percentage here, but it's clear just by looking at the graph. This is the largest slice. Now, what's the worst month for cruise ticket sales? The worst month? Well, then we just have to find the thinnest slice of pie. And if we look over here, slices of pie get pretty thin out down here. This is in the summer in June and July. And in May, smallest are actually July and June. And this is where the numbers become useful because when you just look at it by, when you just eyeball it, you're not sure, hey, are these exactly the same or are they different? And that's where these numbers are valuable. And based on the data they've given us, it looks like these are tied for the worst in turn. Both of these months, they sell only 3% in each month. So the worst months for cruise sales are July and June. July and June are tied for the worst. Best is clearly January, and then after January, the next best, we have the pie chart in front of us, might as well ask ourselves that. What's the next best? Well, it looks like November is slightly better than December, but in general, it's pretty clear that the winter months do much better in terms of cruise sales here away from the cold.
Oh, all right. That's the pie graph. I think that's pretty interesting because in the modern society, people often use a pie graph or pie chart to represent their data. So that's great. And also by knowing those mathematical words, it's not only a help for you to understand the mathematics, it's also a help for you to write some programs that related to the data representations or kind of stuff. If you don't know those words, how can you actually write programs? What are you doing? So you must know those words, and you will often use it when you do that programming. Here we go. This is another video.
What I have here is the list of ages of the students in a class. And what I want to explore in this video is different ways of representing this data and then see if we can answer questions about the data. So the first way we can think about it is as a frequency table. Frequency table. And what we're going to do is we're going to look at for each possible age that we've measured here, see how many students in the class are of that age. So we could say the age is one column, and then the number of students of that age. Or we could even say the frequency. People say, how frequent do you do something? They're saying, how often does it happen? How often do you do that thing? Frequency. Or we could also say, actually, let me just write number. I'm always a fan of the simpler number at age. You could also consider the frequency at that age. All right. So what's the lowest age that we have? Well, the lowest age is 5. Start with 5. And how many students in the class are age 5? How frequent is the number 5? See, there's 1, 2. Scanning. Looks like there's only 2 5. So I could write a 2 here. There are 2 5. And now let's go to 6. How many 6s are there? Let's see. There's 1 6. There's only 1 6-year-old in the class. All right. 7-year-old. See, there's 1, 2, 3, 4 7-year-olds. 4 7-year-olds. Now what about 8-year-olds? 8-year-olds, I'm going to do this in a color that I have not used yet. 8-year-olds, we have no 8-year-olds. 0 8-year-old. And then we have 9-year-old. 9-year-olds, we have 1, 2, 3, 4 9-year-olds. 4 9-year-olds. 10-year-olds, what do we have? We have 1 10 right over there. And then 11-year-olds. 11-year-olds, there are no 11-year-olds. And then let me scroll up a little bit. And then finally, 12-year-olds. 12-year-olds, there are 1, 2, 12-year-olds. So what we have just constructed is a frequency table. You can see for each age how many students are at that age. So it's giving you the same information as we have up here. You could take this table and construct what we have up here. You would just write down 2 5s, 1 6, 4 7s, no 8s, 4 9s, 1 10, no 11s, and 2 12s. And then you would just have a number. Now, a way to visually look at a frequency table is a dot plot. Let me draw a dot plot right over. So a dot plot. And a dot plot, we essentially just take the same information and even think about it the same way, but we just show it visually. So in a dot plot, what we would have, actually, let me just not draw an even arrow there. We have the different age groups. So 5, 6, 7, 8, 9, 10, 11, and 12, and we have a dot to represent, or we use a dot for each student at that age. So there's 2 5-year-olds, so I'll do 2 dots. 1 and 2. There's 1 6-year-old, so that's going to be 1 dot right over here. There's 4 7-year-olds, so 1, 2, 3, 4 dots. There's no 8-year-old. There's 4 9-year-olds, so 1, 2, 3, and 4. There's 1 10-year-old, put a dot, 1 dot right over there for that 1 10-year-old. There's no 11-year-old, so I'm not going to put any dots there. And then there's 2 12-year-olds. So 1 12-year-old and another 12-year-old. So there you go. We have frequency table, dot plot, list of numbers. These are all showing the same data, just in different ways. And once you have it represented in any of these ways, we can start to ask questions about it. So we could say, what is the most frequent age? Well, the most frequent age, when you look at it visually, the easiest thing might be just look at the dot plot because you see it visually. The most frequent age are the 2 highest stacks. So there's actually 7 and 9 are tied for the most frequent age. You would have also seen it here where 7 and 9 are tied at 4. And if you just had this data, you'd have to count all of them to kind of come up with this again and say, okay, there's 4 7s, 4 9s, that's the largest number. So this is, if you're looking for what's the most frequent age, when you just visually inspect here, it probably pops out at you the fastest. But there's other questions we can ask ourselves. We can ask ourselves, what is the range? What is the range of age? And this is once again where maybe the dot plot is the most, it jumps out at you the most, because the range is just the maximum age in your, or the maximum data point minus the minimum data. So what's the maximum age here? Well, the maximum age here, we see it from the dot plot, is 12. And the minimum age here, you see, is 5. So there's a range of 7. The difference between the maximum and the minimum is 7. But you could have also done that over here. You could say, hey, the maximum age here is 12. Minimum age here is 5, and so subtract from 5. You find the difference between 12 and 5, which is 7.
All right. For this kind of scene, as we could know, if we doing the data analysis with the programming, that will be the most exact way or accurate way for doing such a thing, and a straightforward way. Let's say, but for human cannot process that data. So, for human, we would more prefer the graph way to do some analysis. Some people would prefer the text, but as a general rule, people would more like the graphs because it's more direct for them to clearly say how things are going on.
Thrill Soda hired a marketer to help them promote their brand, Yummy Cola. The company gathered the following data about consumers' preference of soda. So they have year by year percentage of respondents who preferred Yummy Cola, percentage of respondents who preferred Thrill Cola, and then these are people who had no. 2006, 80% liked Yummy, only 12% liked Thrill, 8% didn't like either one or didn't have. So here you see that many more people liked Yummy Cola than Thrill Cola. Thrill Cola definitely has something. They have an uphill battle. But then they said the advertising company created the following 2 graphs to promote Thrill Soda. So let's see what's happening. Misleading or not. So if we look at this graph over here, in 2000, sure enough, 80% liked Yummy Cola. Then 2007, 76%, going to then 77%, 73%, 73, then 68. So this is actually accurate data. It actually data that's given right over here. I'll do it. Actually data very faithful. Then right over here, if we look at this chart, percentage of people who prefer Thrill Soda. So over here in 2006, 12 for Thrill Soda, 2006, 12%, 2007, 19%, 2008, 19%, then we go up to 20, 21, 25. So the graphs are actually not lying. These are actually the data of the percentage who prefer Thrill Soda. Now what's misleading is if someone were to just look at these 2 graphs without actually looking at scale, they'll see 2 things. Say, oh look, you see a declining trend, and that's what line graphs are good for. Say, look, I see a declining trend in the percentage of people who prefer Yummy Cola, and I see this increasing trend in the percentage of people who prefer Thrill Cola. And that's true. You have a declining trend here, and you have an increase here. But what's misleading here is the way that they've plotted the scales. These scales are not the same. So when you look at this, you say not only is there an increasing trend of people who Thrill Soda, but the way they set up the scale, that it looks like the trend is above. It looks like if you look, the human brain is tempted to compare these. Say, look, not only is this trend, but it's above this trend right over here. Even in 2000, this data point looks higher than these data points right over here. But the reality is that it's only because the scale is distorted. And this is the oldest trick in the book when plotting line graphs. All depends on the scale. So this just looks good because they used a scale that went from 0 to 30 or 100. The more, the better thing to do, or the more genuine, the more honest thing to do would have actually been a plot graph. Although if they did that, that wouldn't have painted a very good picture for Thrill Soda. So if we plotted it on the same graph, Thrill Soda, let's try that out. So in 2006, 12, and actually this is even worse. You wouldn't even be able to plot Thrill Soda on this graph because they started this graph right over here. They didn't even start it at 0%. So you actually would not even be able to plot Thrill Soda on this graph. If you did, you would have to extend this graph all the way down. You would have to extend this graph all the way down to, it would have to be 40, be 30, be 20%, 10%, then or down all the way over here would be 0%. And then the Thrill Soda graph would be all the way down here. So it was like 12%, goes all the way up to like 25. Thrill Soda, so it would graph nowhere near. If you plotted these on the same scale, on the same graph, then it would have still been pretty obvious that a lot more people, even though the trend is downward, a lot more prefer Yummy Cola. So there's 2 very disingenuous things going here. One is the actual scale for this amount of distance on this scale, they represent 10%. So whatever the gain is. And over here, that same amount, they're actually representing a larger amount. They're 15 or 16. And then the main thing is they started the scale here. So they're not showing how many people really prefer, how large 80% or even 70% really is. And over here, they start at 0 and they just have a larger scale. Look like out the gate, a lot of or comparable amount of thrill. Trend is up, but the reality is still way more yummy. A little bit, actually very not so honest way of
okay, so in this video, the Kehan tell us one thing, that is, if we do the land graphs, we need to care about the scales. You know the scales can be a little bit tricky. If let's say, if two graphs uses different scale strategy, then they are not comparable. If we want to compare two graphs, we need to make sure that they have the same scales, and it's better to print out both of them inside of a same graph. So here we only left 3 videos. Let's have a look at them. I don't know what's inside of that.
Say that today, day one. Day one is what I want to figure out is what is day 300, what day, write out the day, Monday, Tuesday, Thursday, Friday, Saturday, and we had a lower number here. We could just fill out Monday is day 1, Tuesday is day 2, Wednesday, 3, 4, 5, 6, 7, and I'll keep going. Day 8, right, 12, 14, kind of useful. I could just write it out if I want. This isn't that helpful if I want to out day 3000. Can I come up with some mathematical way about what day? Well, as you see, when I started drawing this grid has rows. Row, you have 7 days a week. So is there a way without drawing this grid that you would know is a Tuesday? Well, one way to divide 16 by 7, I will tell you how many of these rows come before. Tell you how many rows divided by is 2 rows before 7 and 9. You have a remainder. What is the remainder when you divided by 2? 2 times 7 is 42. So when we divide, we've historically cared more about this. We normally care more about, well, how many times does it go? Now the remainder tells you, the first 2 just tells you, well, 7 goes into rows, but then the remainder tells you, well, in that row, where is 2? In the 3rd row, so it's going to be a Tuesday. Tuesday is day. I know what you're saying. Does that always work? Well, let's try it out with some other example. Imagine day by 25, right? I have 7 goes 3 times 7. So based on that, 5 divided by 3. So based on this, if we were to write out the grid, we should have 3 rows of 7 before we 25. So if it's sitting in the 4th column, it'd be a Thursday, 35 should be a Thursday. That actually 1, 2, 4 is indeed a Thursday. 7 rows for the row, and then in that row gonna be the 4th row. 1, 2. Now we're ready to day 7 goes into 3rd, 4, 2, 7 goes. Then we get our. Now we care much more about the remainder. So our remainder is 6. So if we think about what day of the week it is, row and column, 42 rows above, we care about is row. So day 3, day of the week.
Alright, at least from this video we have learned that the factor has meanings. It could help us to get some information from let's say from a repeated pattern.
I want to make little town. Be my first 3 bar 4 5. Let me make a little table here. The number of, and this is, so this first house here. Me 6 2 3 4. Make our, these are going to be town. Share common wall. I'm going to add 1 2 3 4 5 house. Now why did I only have to add 5? They shared a common wall here. Add wall. So starting with the first house, I really just had to add 5 to now 11 total. 2. I want 2 houses. Trend here. What about 3? What about 3? Well, this is going to be another 5. 1 2 3 4 5 2 and 4. So fourth one, we're gonna add another 5. 1 2 3 4 5. Fourth one, we're gonna add another 5. 2. Now I want to think about, can we, using this pattern, figure out how many it would take for us to say make 50 of 500 of 5,000. We just pattern here and see, can we equation for each of these actual values? For example, the pattern that, well, we already recognize that we're adding 5 to, so when you add the second house, you add 5 once. The third house, you add 5, you add 5 twice. Fourth house, start with 6 and you add 5 3. You write 21 is equal to, you start with 6, start with 6, and then you add 5 3 plus 5 3. And you had the 3 house again, started with 6, and you added 5, 5 2. When you had 2 house, started with 6 and you added 5 1 5. And then when you had 1 house, when you had 1 house, same pattern, you started with 6, and how many times did you add 5? Well, you didn't add 5. You could say that you added 0 times. So you might see a little pattern here. However many houses you needed, take 1 less than that.
Alright, for this video, I can even write out the rows for you. For example, at the beginning, you have to use, let's say, 6 toast packs, right? Then, let's say for each house, you would need, let's say if you have you have X houses, and for each house, you will need to use 5 more toast stacks. So in the end, you will get an equation like this. So let's say here he got 1, 2, 3, 4. He got 4 houses. So that would be 6 plus 4 times 5. That would be, let's say, 26. Was that correct? No, it's not correct. We should minus it by 5. So here for the x, we should do some changes for it. It should be x minus 1. Alright, that makes sense. Now, if we minus 1, or if we change this number to 3, we would immediately get 15. Plus 6, which is 21. Awesome. So we don't have to watch this video anymore. Let's just jump it. Let's go on to the next video.
So let's say I have table where I can fit one person at either of the short, one person view that from above the table, one of the short, and then on these longer fit 2. So when you have one table, you 5. Now let's think about what happens. Add table end to end to this table. Imagine now, so table end right over here. Because it touches ends right over here, we're kind of making a continuous table. Someone here. So now how many? 1, 2, 3, 4, 5, and then on this table, which is identical, you 6, 8, 9, and then you could put one person at the end. Here, when you have 2 tables end to end, you can now 10 people going and see. So let's put 3 tables. So 1 table, 2 tables, and 3. So just as before, we could put 1 at each end, so that 2 people, 3, 4, 5, 9, 11, 12, 13, 14. So what does it look like is half the numbers? We went 10 to 14. It looks like we're adding 4 people. That actually makes, about this first, imagine these are real people, and I'll make, if you were to bring over new table, bring over table 2, table 1, bring over table 2, this blue person has to move. So where could they move? Let's say that they always, hey, blue person moves to the new, they move right over. How many new people could move to combined table now that you brought the new people? I will do new people are that person, and so you were able to add 4 new people with a new table. One way to think about it is a new table is going to have one usable end. Usable end is going to be taken by the person who was already at the usable end of when you had less tables. So you're really able to, the real addition is the 2 sides here. So you're adding 4, so it makes complete. So based on this, think about, without even having to draw these diagrams, what would happen? Or you had 4 or 5 or 6 or however many. So you can imagine if you have 4 table, and you should be able to sit. You have 5 table, be able to fit 22 on.
Alright, it's just a simple way to let's say the author of this video just showed us the basic strategy for finding patterns through number changes or something like that. Okay, this is quite simple and probably useful. I don't know. Anyway, yeah, it's useful. It's always useful to find out common rules from science. That's the science where the science comes from. Okay, so let's say this is today's tutorial or video or learning video. Inside of this video, we have talked about how to reading and representing the data in different forms, or display those data in different ways. And those are basics for you to understand data, because in the end, if you do programming, you would likely to handle data very often. So if you don't know the idea of the data, you probably won't be able to do it. So that's today's learning. I will see you guys in the next video. Bye. Have a nice day.